A couple pretty important definitions in chapter 4 are those of a prime ideal and a maximal ideal. But I think especially with maximal ideals, the definition is kind of hard to understand. Let's think about prime ideals first. It's a little easier. A proper ideal A of a commutative ring R is a prime ideal if A times B being an A, where A and B are ring elements, implies A is an A or B is an A. Let's think about this with examples, and let's keep the example simple and maybe try to understand why it's called a prime ideal. The example is to let the commutative ring, be the integers. We do know that this notation represents what we call the principal ideal generated by the element n. Let's say n is an integer. It's same kind of notation as cyclic subgroup generated by n. If we were thinking in terms of group theory, the cyclic subgroup generated by n would be all things you can get by adding n to itself over and over again, along with 0, along with adding negative n to itself over and over again. It would be all multiples of n. We talked last week about how that's actually the same thing as a principal ideal for the integers. It's not the same thing for other rings. I'll remind you of an example in a bit here. As a principal ideal, it's all ring multiples of n, but those ring multiples are integer multiples. And because of that, that's why you get the same thing as the cyclic subgroup generated by n. Because the ring multiples themselves, the elements are integers. So I get, for example, n is 1 times n, 2 times n, 3 times n, 4 times n, etc. 0 times n, -1 times n, -2 times n, -3 times n. I'm taking arbitrary integers and multiplying them by n, I still get another integer. That is still a multiple of n in the ordinary sense. Just like I'd get if I added n to itself over and over again, also include 0, also add negative n to itself over and over again. You might wonder, is this a prime ideal or not? The answer is, it depends. It depends on whether n is prime or not. If n equals p is prime, is the resulting principal ideal generated by that p a prime ideal? If p is a prime number, you would hope so. Otherwise, why bother calling it a prime ideal in the definition of a prime ideal? Let's explore a little bit. Would this condition hold? If I had the product of two things being in this ideal right there, does that mean one or the other element is in the ideal? Suppose AB is in this ideal generated by P, this principal ideal generated by P. Does that mean A or B has to be in there? What does it mean to be in the principal ideal generated by P? It means you are a ring multiple of P. There exists an integer n in the ring, which is the integers, such that AB equals n times P, right? That's a ring multiple of P. What does that mean? Think back to chapter 0. Another way to write this is to say this means P divides A times B. And what pretty fundamental fact in chapter 0 did we have? It even had a name after an ancient Greek dude for what happens when you got a prime dividing a product. What can you conclude? Remember? Yeah, it divides either A or B. What's the ancient Greek dude's name? Euclid. Yeah, Euclid's lemma. You got it right. In other words, either A or B is a ring multiple of P. I could add on that this means, okay, there's either an M such that A equals MP or an N such that B equals NP, or use a different letter than N since I already used an N. But I don't really need to. This means A is in the principal ideal generated by P, or B is in the principal ideal generated by P. Therefore, the principal ideal generated by P is a prime ideal when P is prime. You might also wonder if N is not prime, is the principal ideal generated by N not a prime ideal? And the answer is to that is also yes. What do we need to do to prove that? Just come up with one example. Back in the chapter about divisibility, we know 6 divides 12, which is 3 times 4. But 6 does not divide 3, and 6 does not divide 4. This does not contradict Euclid's lemma because 6 is not prime. This would be equivalent to saying 12 is in the, or 12 equals 3 times 4 is in the principal ideal generated by 6, but 3 is not in that principal ideal, and 4 is also not in that principal ideal. 3 times 4 is in the principal ideal generated by 6, but neither 3 nor 4 are. That's enough to show the principal ideal generated by 6 is not a prime ideal. And you could come up with examples for other non-primes as well.